Let us now look at a new class of binary star system known as eclipsing binaries. You see, if you have seen the previous videos, we were measuring light as a function of the position, which changed as a function of time, or as a function of the spectrum. And in spectroscopic binaries, the spectrum changed as a function of time. Right? Now we are looking at a class of binaries where the total flux changes as a function of time. Right? Of course, this has to be a very small subset of all the binaries that we see. And the simple reason is that it needs to be oriented only at a particular angle with the V of sight, such that the plane of the orbit is parallel to the line of sight. When that happens, the objects which are going around each other in certain part of the orbit, one object will obscure or occult the other object, and in the second half, it will obscure or occult the first object by the second object happens. Okay. So the number of such binaries will definitely be less, because if you take the random distribution of the orbital plane in three-dimensional space, then there will be very few numbers of binaries which are exactly parallel to the line of sight. And it may happen that it is not exactly parallel to the line of sight, but as the objects are going around each other, maybe fractional occultation can happen. Okay? So fractional ellipse can happen, and hence the eclipse will result in a reduction of the total flux that you're receiving. Simply because when the two objects, they are not obscuring or eclipsing each other, you measure the flux from both the objects. The moment one comes in front, you are blocking the flux from the object that is behind. Okay? So this is how the system looks like when you are looking at the plane from the top, and this is how the system looks like when you're looking at the plane edge on. So you can very well see that if this is my time axis, right, and this is the total light that you're receiving, okay, so this is the x-axis which gives the total light. 0 is here, okay. So this is how the light as a function of time will be observed. When both the objects are visible to you, you get the total light from them. When this object is coming here, starting to eclipse and reaches here, okay, so this is known as the first contact. When this particular surface touches this surface, this is where the eclipse starts, and the total light keeps on diminishing until the second contact happens, where the back surface of this red star has reached the surface of this yellow star. And then, as long as this smaller star is transiting the surface of the larger star, you get this much of obscuration that is happening. And then when the third contact happens, your light curve starts increasing. When the fourth contact happens, it again reaches the maximum point where you can see both the stars here. Now, when this star now goes behind, you again see the obscuration that is happening out here. But mind you, it is very important to understand that if the stars are not of the same style, here you can see that again you see the maximum amount of light from both the stars which are here. Now, you have to be very careful that when this red star, which is a smaller star, goes behind, then what happens? it'll again, the total flux reduces, but the amount of reduction is not the same. Simply because the amount of light emitted by the two objects are not the same. If these two objects are exactly of the same type, then the amount of emitted light from both these surfaces will be same, and hence when either of them gets obscured, the same amount of reduction will happen. But if my larger star has more luminosity, then what will happen? The amount of light coming per unit area from this surface is more, and hence when it gets obscured, the amount of light blocked from this area per unit area is more. And hence, although the amount of area that is getting blocked is same when this star is front or back, the amount of light that is getting blocked is different. And this causes the difference in the amount of light that you see when the eclipses occur. And this also gives a measure of the physical parameters of the binary star system. Okay, this is the figure of exactly the same thing, but giving a slightly more detailed. Okay, so look at this star system that you have out here. This is your blue type B star, okay? So, and this is a star A, this is a star B, okay? One corresponds to this region where the bright light from both the stars are there. This is the line of view of the observer, and this is what the observer is seeing, right? Mind you, you may or may not be able to resolve the two-star system, okay? It might happen that these two objects appear like one point source, but the total amount of light is changing as a function of time, okay? So, when the two stars are not eclipsing each other, you see the bright light from both stars, then this is the first contact. This is where your light starts diminishing. And when up till the third contact, from this is the point of second contact, this is the point of third contact, okay? So this is where the light again remains constant, the flux remains constant. And now as this star is going away from the field of view of this star, okay? So basically this two region starts here, corresponding here, and 3 is this region. 2 is the first contact and 3 is the third contact, okay? This is what is correspondingly happening out here. Then 4 is this whole region where you see the bright light out here. And then 5 is the point of first contact when this star A is going behind. Again, the total luminosity diminishes, but since this star is emitting less amount of light, the amount obscured will also be less. And hence, this region 6, from 5 to 6, you see this is the first contact, second contact, this is the third contact. And from the second to the third contact, it remains constant. Less amount of light is diminished, but it is diminished. And then again, it reaches this region out here. So now from here, by measuring the extent for which you see the eclipsed condition, you get a measure of the relative sizes of the binary star components. Once you have an handle on the relative sizes, then you have the handle on the spectral type, the luminosity type, the mass type, and everything else. Okay? So this gives you an independent set of measurement for the binary parameters. So it might happen a particular binary can be eclipsing also, can be spectroscopic also. can be spectrum binaries also. If that happens, then you are very lucky. You have independent set of measurements to measure the quantities of the parameters. Okay. So ultimately, our understanding depends on all the parameters that we can measure and iteratively put in the equations and then get a complete picture.